All right. Hey, everybody. Glad to see you here virtually. Sorry I couldn't make it to ZDS this year. Unfortunately, things just didn't line up with schedule purposes, but I'm here to share with you some learnings that I've had over the past year since the last conference or the last developer summit, and also yeah, we're just going to jump into some my favorite topic of basically having this code base and the power of Zephyr, and then using that same code across different hardware devices and boards and architectures. So that's what we're going to be talking about today. So let's jump into the slideshow here. I actually follow this very similar format. If you've ever seen it in my videos, you can check out youtube.com/c/circuitdojo. Do a live session every week talking about Zephyr. So, and specifically your questions. So folks reach out, send me an email, leave a comment, they hey, how do I do this? How does this work? And you know, whenever I get like multiple of the same message, I'm like, okay, this is probably a problem we should talk about. So definitely check out that channel, click that subscribe button, and join me every week. Right now it's been Thursdays, but we're going to be doing it back on Tuesdays. Tuesday afternoon Eastern time is kind of the standard. So that'll be starting back up next week. But let's dive into the content here today, and we'll go from there. So designing for multiple targets, that is one of the core tenets of Zephyr. And literally to build on a different platform, if it's supported, it's literally just changing a board type, and it just kind of works magically, which is really nice. Now, the thing is, there's an asterisk up here in the corner that with anything in Zephyr, it needs to be supported well. It needs to be supported in the first place, and the features across the platforms need to be equal. So we'll dive into that a little bit, but specifically, and this is the biggest thing that I ran into, that last line there, it requires a lot more configuration than you would expect, and troubleshooting and things like that. So we're going to jump into it a little bit. But first, of course, do your research and make sure that the device that you want to use is going to work with the code that you're trying to use. So say you have an example, we're going to be working on a specific air quality sensor board that I built, but it could be anything really. And you just want to make sure that the support is there on the hardware application layer, the HAL layer, for your board, your device, or any of the other devices you're using. Maybe it was built for a specific device and you're like, oh, maybe I can use it on mine. You just need to make sure that both of them are compatible at the hardware level, making sure you have the right UARTs, I2C, things like that. I've been burned in the past in terms of, like, for instance, like a ESP32. They have some Zephyr support. I don't know, they're trying to push more, but when I was playing with it, I was like, oh, my client needs an I2S support for microphone. And I started developing, and I was like, all right, now to hook up the I2S. And I was like, oh, there's no I2S support in Zephyr for this particular part. So I was up a creek without a paddle. So that's just like something that you just need to check before you start any work, because it just saves you a lot of headaches. In this case, for this sample, we're working with I2C and UART. Those are the most basic peripherals that you're going to be using on any microcontroller. So fortunately, all the boards here, all the processors here support that. So we're already ahead of the game here. So speaking of, for this presentation, we'll be using 3 different boards and chips. The NRF9160 Feather, which is based on the Nordic NRF9160. Particle Xenon, which is kind of my standby for the NR52840. And a completely unrelated, non-Nordic chip here is the LoRa E5 Dev board, which is from Seed Studio. I just happened to be working on it for another project, and I was like, this is a great example of something. All these processors, I believe, have different, they all have different types of Cortex whatevers. They aren't different architecture, so but this should give you an idea of like, hey, I can take a completely different processor. One has a LoRa radio, one has a Bluetooth radio, one has a cellular radio in it, and they all can run the same code with some finagling, of course. So for these guys, originally I was going to do feathers, but there's feathers plus this other LoRa dev board that I'm using, and I'll show you a picture of that in a second. But we're using one UART, one I2C, and a couple of controlled GPIOs. So those will be our interfaces that we're working with. And then here is the Xenon with the kind of the prototype air quality wing that I have here. This was an older picture that I took, but it gives you an idea. Like literally, you just put them in a doubler, and you got a working subsystem, a system here. Here is the LoRa setup. It's a little more intensive in terms of using some wire jumpers between the air quality wing and the dev board. That's because I just didn't really have any other boards to try with this. So, but they both work the same, which is nice. And of course, the purpose of this is to, with the air quality wing itself, to measure PM 2.5, which is particles in the air, smaller than 2.5 microns, and temperature, humidity, and VOCs. So, and the temperature and humidity values feed into the algorithm for the VOC. So that's also very handy because it's all right there on one board. So, and I'll show you that in a little bit. So, but here's an example output of what we'd expect from everything once it's actually running. There might be some warnings at the beginning when it loads up, but it should be plunking along on each of these boards and their unique communication setups. So we'll get into that in a second as well. So, but this is what we expect to be running on every single board. And by the end of this, I'll show you that that's going to be the case. So, but the first thing, and this part is probably the most important. This is a thing that that solves a lot of problems between many different kinds of Zephyr distributions. So Nordic has their NRF Connect Studio, and that's great, and it works well for Nordic parts. But if you start using it for other parts, you're gonna have issues. I ran into problems where I was like, okay, I don't need it to build the bootloader because it automatically builds the bootloader for those boards. In this case, it was not playing nice with the LoRa chip, so I had to figure out a way to deal with the two disparate kind of setups. So what happened here is I did something that the folks at Goliath did with their SDKs. They actually created two different manifest files. One manifest calls out kind of like the vanilla version of Zephyr, which is just Zephyr straight up, and then one then covers or calls out the NRF Connect SDK. With these two things, what you can do is you can initialize and set up your environment for one setup, and then if you have to build for the other one, literally it's just like changing a file and then reinitializing for the other setup. So we can jump between the two, and I will show that in a little bit, but it's kind of powerful because you can keep your same setup. You don't have to create a different repo. None of that nonsense. Everything can live here, and then all you have to do is just literally run a West update, and you can be in one setup and then transfer and go to the other setup and build for different targets that don't quite play nice with each other if they're both enabled on the same SDK setup. But you can see here, like I mentioned, the two different kinds, and biggest thing is it prevents any type of build conflicts or things that might happen for one piece of hardware and might not happen for the other. Like for instance, building the bootloader doesn't work, or if you try to turn it off on NCS, it won't let you do it. So things like that. So here's here's the basics of an NCS one. You're importing NRF Connect, setting the version and things like that. You also might notice for this particular demos repo, I also have some other repositories for like the air quality wing demo or the drivers, and also the underlying library code. So all that lives in a different library as well. So that gets pulled in no matter what. That actually stays constant across these manifests. What doesn't stay constant is what SDK you're using. So at the top of this file, we're using NCS. At the top of the next file, we're using vanilla Zephyr. And I'll show you that here. So Zephyr 3.0, and then of course importing some specific name, submodules, Zephyr submodules, specifically SD, things like that. And also, when you do, I wish I could point this out later, at the bottom here, the name import list, this is great because Zephyr can get pretty big. For instance, if you're pulling for NCS, for instance, if you're using a project that, or if you have a project that's not using something like OpenThread or Matter, that takes up a ton of space and it takes forever to download, and also has a bunch of sub dependencies, which makes just setting up a repository really slow. So that will allow you to basically exclude those from any updates, so you don't have to download them every single time. Kind of speeds up the development cycle, speeds up the setup cycle. So that little thing, like, definitely check out more of the documentation on the West manifest, because you can really hack these things and tune them to make it really simple for your projects, which is thumbs up. So switching between the two manifests is fairly simple. Once you have everything set up with one, you can edit your .west config file, and you can literally change the name of the manifest file, and then you can run west init and west update to actually kind of pull your requirements. And what this will do is it just recursively pull everything depending on your the hash of each. It will pull that specific snapshot of that particular repo and just go through and pull everything. Sometimes they're the same, sometimes they're different. In this case, almost for between the two different files that we're using here, it's pulling a different version of Zephyr SDK. So that's just like, it's great, because you'll see in a second, it's just like, wow, I just changed a whole complete set of dependencies with just one update command, and I can just go back if I need to. If I want to compile for NRF, I'm here, or if I want to compile for this STM32, it's pretty straightforward. So, but the biggest thing is making sure to run that west update command when you do it. And here's the file itself. I'm just showing you, like, hey, let's change this here. This is the most important part that you're going to be working with. Let's get the design to work. So the base code should stay the same. So in your main file, almost everything should stay the same. Now in this particular project, I had to change one thing, and that was for if you're using the Xenon, or if USB is enabled, it will enable USB. That's the only thing that I changed, since I kind of tooled around with this to make sure everything worked on the 3 different boards. So besides that, the base code, the driver, everything else should work across the different platforms, which is nice. The caveat is you have to make things compatible depending on your configuration and your overlays. And if you ever watched any of my live sessions, those are the first things I talk about. Those are the first things that you really need to make sure are correct, or things are not going to work. The wheels are going to fly off the wagon. So we always go through the overlay and the configuration to make sure that those things are set up and they're correct, because they're the things that are going to be dictating how this particular code is going to run or compile, if at all. So important caveats. But the thing is here, overlays will get mushed into your application. So if we're using in this case, we're kind of using the basic application that is connected to the air quality wing. And the important thing here is those definitions on this side of the application, everything kind of gets mushed together when you're actually building with a particular board, and it's dependent on the overlay and the configurations. So if you're a veteran to Zephyr, you already know this, but for someone who's coming in, it's like, all right, how do I only enable USB for one board, and how do I make sure nothing else is turned on for another one? And everything, in this case, it's all controlled by those overlays and configuration files. Here they are. If you look in the demo folder here under basic and then boards, you can see the overlays and the configurations. And this is the default location that Zephyr will look for these files. So if you don't put anything there, not a big deal. So if you're just targeting a specific file, it's going to be using the defaults provided wherever your board is defined. If you need to make changes, you can make them locally there. I recommend, that's why these overlay files exist, because you can start with a kind of a sane default, either in the Zephyr repo or in a out of tree repository where you can actually define a board. Nordic actually did this in theirs, where they define a couple boards that don't exist in the higher level Zephyr, vanilla Zephyr repo. So you can kind of pick and choose where you want it to go, but generally at the application level, you have the same default setup, and then you can kind of create your configurations and your changes at the application side, on the application itself, using the overlays and the configuration files. So hope to not make that too confusing, but biggest thing is here is you want to go into that boards folder if it exists, and that's where all the action is happening for this. So we'll talk about the commonalities. So the things that should look the same is like the sub-device labels. So we're talking about like the temperature sensor, the VOC sensor, and the HPMA, the PM 2.5 sensor. And also because those names are the same, we're also using the same kind of the compatible entry, which basically, if you've ever seen, and we'll go into it in a second, but if you look at the overlay and it has a compatible line, that's the line that calls out the device binding for that particular driver. And in this case, no matter what, whether we're using NRF52, NRF91, or the STM32, we're all using that same binding. So important thing to note, those are the commonalities. Now, the point of these overlays and the configuration files, though, is because of the differences. So we'll get into the differences next. But first, here are just the commonalities. You can see, if you look across all these overlays and configuration files, you're going to see these common similarities between them. You'll see the SGB40, SHTC3, HPMA, the HPMA guy, which you can't see, it's kind of off screen. So those are the commonalities. Differences. The differences include because we're working with different processors, not all of them are going to have I2C 0. Some of them have USART 0, things like that. So some of them have DMA, where some of them don't, at least explicitly called out. The Nordic chips have the easy DMA, quote unquote. And using you're going to be using device-specific bindings in the compatible entry. So like I said, for the drivers, for the devices themselves, like the SGP, they're calling out the device binding for that specific driver, whereas if you're putting it under a I2C or UART, you're going to be calling out the chip-specific binding for that thing. So STM32 has a specific compatible binding for their USART versus Nordic. Nordic has their own compatible binding for that. So that's where we're getting into the differences. We're actually starting to call out the STM32 UART driver versus the Nordic NRF52 or Nordic NRF9160 UART driver. Actually, the UART driver for both of those guys, the NRF52 and the NRF91, are the same. They're the NRFX USART. So both in this case are the same. Zoom in again, and we'll get to the VS Code in a second. We're almost done here with the slides, at least. So we talked about the compatible entry and then the pin mappings. So for any GPIO controls, those pin mappings are obviously different. On the NRF91, the ports are labeled by number, so you have port 0 and port 1, specifically for the NRF91, or the NRF52. NRF91 only has one port. For the STM32, they've always gone by letters, so you have port A, B, C, D, E, so on and so forth. And the interesting about the STM32s is that you're going to have multiple different ports on a chip that's only got 64 pins, 48 pins. So you'll have port A, port B, port C. They're all kind of scattered and reused about. The bigger the chips, the more likely that you're going to get a full port to be used. But in this case, just remember that there are differences here that you just have to account for, and they're just like things you have to think about. It's like, okay, I'm working on an NRF90 or NRF91. I have port 0. That's it. So you're working on GPIO 0, and then you have the pin number. If you're working on STM32, it's like, okay, now I need to check the port. It's port A, pin 9. Okay, got it. You're just going to make sure those things are correct in the overlay, or else you're just going to have issues. One important note there also is when you're using GPIOs, you're just going to make sure you look at the schematic for that board and make sure they're not being used for something else. I originally used A9 on the lower board because I was going to be controlling the power for the HPMA PM2.5 sensor. Turns out it's also being used as the GPIO control for the 5 volts, I believe, 5 volt output on that dev board. So that was not going to work for our case. So it's just something to keep in mind. Otherwise, in this case, otherwise it would have just kept the HPMA sensor on all the time. It wouldn't have worked. So there's things you need to know. You just need to know your hardware. You need to know and then you got to know the basics of your hardware application layer and the firmware to make sure that things all work together. So here are some of the differences I mentioned. So this is the configuration file for the particle xenon. I actually enabled usage of USB here, and that actually opened a can of worms of like working with the onboard USART because each of them you have an emulation of a UART on USB, so the two just needs to play nice together. And in this case, I just enabled USB, and also I just had to do some finagling with the UART 0, making sure that async is turned on, but also the interrupt-driven stuff is turned off. But you need the interrupt-driven stuff turned on for the USB. So you can definitely, I'll have a link to this. All the code is open source. I'll have a link to all of this so you can check it out on your own time, and everything will be there so you'll be able to check it out. But that's just one thing. Here's one big difference that I found with the particle xenon. There's a whole bunch of stuff that have to happen here only in the configuration file. Now there's even more in the, there's some in the overlay, but in the LoRa chip specifically, there's a whole bunch of stuff going on there that I had to figure out, which took me a lot longer. So we're enabling the async API for UART, configuring, enabling USB, and also just the coexistence settings between UART 0 and USB. Specifically the UART interrupt-driven versus async. And one important thing, I'll show, it'll come up in a second, but the async API is used by all 3 chips, fortunately. Now, if you had a board that maybe did not have the async API, that's one thing that the current air quality wing driver uses. So if you don't, then your board would not work with the air quality wing. So that's just another thing. You would have to kind of look at the code. It's like, okay, I need the async API for this, so I need to make sure that it's actually supported by the hardware platform I'm using. Here is the LoRa E5 stuff. So the big difference between this guy and the Nordic stuff is that the Nordic stuff, all the DMA is all abstracted, so you don't even have to turn it on, you don't have to worry about it. It's not even a thing you have to think about. For STM32, it is something. So you need to make sure you're enabling DMA and then also enabling the STM32 DMA specific items, and then also I believe it's all done by default in the background, but I was just doing it for good measure here, and it's done within the kconfig of the async UART stuff, but why not? And also enabling UART for STM32 and the async API. And then one other thing is that the Nordic stuff, you can only set the MCU boot, and it will automatically merge and build your bootloader, and it's awesome. For vanilla Zephyr, you actually have to build your bootloader, program it to the board, and then you're building your application separately, and then you're loading it over New Manager. You can, or MCU Manager I should say, you can merge these files together the two hex files. It's not that big of a deal, but you can check out how Nordic does it. That's just a bunch of CMake magic that makes it happen at the end of the compilation process. So, but in this case, I needed also to include the signing key, which is just the default one that comes with Zephyr, just to make things at least a little bit more simple, just for testing purposes. Like I mentioned, requires DMA, and then DMA also requires some manual configuration, which this is probably what threw me for the biggest loop, because I wasn't used to configuring or setting it up. For them, they have these the idea of a slot, a DMA slot. So you have a DMA channel, and a DMA slot. Channel is just like, hey, I'm dedicating this particular piece of the DMA hardware for something. The slot then tells the software, okay, I want to connect the DMA to this hardware peripheral. So I had to figure out the number of the slot, which I think the RX is 21, and the TX is 22. It'll be in the next slide. But those numbers were important, and it was a painful experience to get it to work the first time, because I was like, why isn't this working? There wasn't a lot of examples or explanations in the vanilla Zephyr repo exactly how these numbers worked or what they did or anything. So it's like the wild, wild west, and I know many of you have gotten frustrated because it's just like, there's not enough details, and this is a prime example of like, man, even for someone who's been doing this for probably working on Zephyr in one way or another for about 2+ years, it's still painful to go from one hardware platform to another, because there's always little asterisks and little things that are little tweakers that are just like, what? Like, how do I do this? Why is it taking so long? This shouldn't take so long. So it's just the way it goes. But once it's working, that's awesome. And like I mentioned before, different P handles, since these are different, different processors, different hardware application layer. And the cool thing is, even though you might have an I2C2 or USART 0, USART 2, or USART 1, they all work out of the box with the driver, the air quality wing driver, because what it says is, hey, I'm looking for something that is using the compatible binding for this, and then get me the higher level device it belongs to. So it doesn't even care. Like, I'm not specifically calling out USART 0, UART 0. I'm calling out what is attached to the device that's already being declared in the overlay. So that is cool. That is something to be excited about. All right, next step. So here's the DMA declaration, and you can see DMA mux. So we're using the DMA mux. I think that's the only way I really got it to work. I tried originally using directly DMA 1 and DMA 2, but they were not working. So you can see I'm using channel 11 and 1. I'm using slot 22 and 21. So the first one is declaring the TX channel, and the second one is declaring the RX channel. That last hexadecimal declaration there is actually all the bits, the control bits for how you want to use those DMA channels. Like if one's a memory to peripheral, peripheral to memory, blah, blah, blah. So that actually required, there was some, I think in the kconfig that's related to this, or the binding related to this, there's a good kind of chunk of documentation that like, hey, bits 9 through 11 are this, bit 12, bit 13, so on and so forth. So it kind of gave me an idea. I could kind of reverse engineer some of the other examples of how people did it in the Zephyr repo. So in this case, this is the way I got it set up and working with the HPMA 115S0. So it's a bumpy road, but once you get over the road to the pavement, it's pretty awesome. And you can see, I kind of belabored the point here, but you can see the different P handles. Actually, I'm using the low power UART, so LP UART 1, and I2C2. That should look familiar, but every board has something a little bit differently at the down level, or the low declaration of like what it has. They might be named differently, so you just gotta keep that in mind. And enabling all the DMAs. So that's just something that the STM32 needed that the NR52 devices didn't. So as for building, choose your target and make sure that it's supported by both the kind of whatever you're trying to connect it to. So you have your main application. Just make sure that it's somewhat supported. It's using the same type of peripherals your device has. And one thing that I might be getting into maybe in the next live session is creating your own board definition. So say your board doesn't exist in Zephyr. Well, how do you get it? How do you get it in there? So when I started working on this for the NRF9160 Feather, I actually submitted my board definitions to and uploaded them to the Zephyr vanilla repo, so it kind of survives. It's there, and then every time someone downloads Zephyr, my board definitions are there, which is cool. But the cool thing is, you can define your board definitions out of tree and then import them or use them in your applications as needed. There are some trickery there that you're just going to make sure that you're referencing those board definitions, but it's a cool topic, and I'll probably go over that in a future live session very soon. The big thing, if you're switching between targets, besides doing the stuff with the West manifest, is making sure that you're doing a pristine build, or you're basically going to delete that build folder and then build again. Otherwise, if you try to build, it will start referencing the NRF52 when you're trying to build for NRF91, or if you're trying to build for the STM32. So important, and it will screw you up if you forget to do that. So let's jump into VS Code here, and I'm going to see what is loaded. Config. Oh no, I want to go to West config. So right now I'm using the NCS variety here, and you can see that it is already set up. So what I can do is I can just init the repo just one more time, and this will actually just do a West update, and it'll also pull any of the Python dependencies. I am using my quick plug for those who might find it useful. I did create a, where are you? Here it is. Circuit Dojo Zephyr SDK tools. This is specifically kind of tailored to the NRF91, but I'm trying to make it more generic for any other boards out there. So it sets up your SDK. It works with any version of Zephyr, which is nice. And it's just another tool out there. I know other people have different philosophies. They want to put it in containers or anything like that, but it's just another option. And it is, at this point, it's supported on Mac, Windows, and PC. Mac is an asterisk because, unfortunately, M1 support for the ARM toolchain is not great, or it doesn't exist. So if you have an M1 Mac, I'm sorry. But you can put it into a VM or something like that, and you could have, a somewhat working development setup for Zephyr. So if you're using ARM chips. But we'll jump into this. I'm going to change my board. So all this does is select the board that I want to use. I'm going to start with the NRF52, which is the Xenon. And I'm going to do a pristine build. So you can see here, I was just, if we zoom, can I zoom in? We're just doing that build with the -P flag, which is just for a pristine build. And I already have it hooked up here, so if I jump over to this guy, camera. So I have a NRF, let's see, what is it? NRF9160 dev kit. And I'm using that as the programmer for this setup. So we have the air quality wing, latest and greatest version in, what was it, Peach Cobbler, and also the Xenon here. You can scan and do whatever you want to that QR code. It won't do anything anyway. But rest in peace. But yeah, it's all set up here. I'm just going to hook it up to the programmer, and then we'll go from there It should be built by now, which is awesome too. But you can see I have it hooked up to USB, and it'll actually, I'll have it set up so it actually connects right to the serial monitor when it's done programming, which is sweet. And I'm going to switch over back to switch cameras and flash and monitor. So it will flash it. And I've already, I think I left off on this, so I've already set up the serial port correctly, so it will start picking up here. So it's already got the temperature, humidity. It takes a minute to get the VOC readings, and it just got the PM 2.5 reading from the sensor. So the goal here is to get now 2 separate boards that are pretty much unrelated, that require separate configurations that we've already configured to compile and run the same exact application. So I hope at this point, since we talked about it, that you're pretty confident that you could even do this yourself. So back to VS Code. What I'm going to do now is change my board to the NRF9160 Feather. I'm going to close out the serial port. Oops. And I just changed to the wrong board. That's okay. So since we're already using NCS, I don't need to change any of the WES configuration files. That will be needed for the STM32. So I'm changing the board type here, and then I'm going to do a pristine build, and then we'll see if there's any errors. I might have to clean it first. Dun, dun, dun. So this will chug along. This one's a little bit slower because it has to build a couple different partitions, images. Well, we should be good to go. In the meantime, so this all I'm doing is running this basic sample, and then you can see I've added a couple different boards in here, the ones that are different, but I'll show the Xenon again. We already kind of covered it, but you can see all this stuff here was to make sure that the USB wasn't going to conflict with the UART0. Originally what was happening was I had USB working and it was displaying the logs, and then the second UART0 actually started doing anything, everything locked up and stopped working. Like, what is this madness? So enabling UART0 helped with that. And you can see here for the Xenon overlay, literally we're just setting the 2 P handles. You can see the different compatible definitions here for Nordic specific. We're setting the speed of the UART interface. That's important for this particular driver, and also you can see we're setting the different GPIOs. In this case, NR52 has 2 banks, so I'm using bank 1. There's bank 0 and bank 1, and then pin 8. On the HPMA, I'm using bank 1 and then pin 10. So, and that stuff I've set up a long time ago when I first put this stuff out, so it still works today, which is great. Alright, so it's done building. I'm going to disconnect power from this good stuff, and I'm going to pop in the NRF9160 Feather. Ta-da! And I need my trusty USB-C cable, and I'm going to put it into bootloader mode. So in this case, I'm actually, instead of using the programmer, I'm loading it right over bootloader mode, which is completely different, right? Like, first I'm going to be flashing one over, over SWD. Going to be using the bootloader for this one, and also using the bootloader for the last one. So all a little bit different, but the same, right? So let me plug this in. I'm plugging in the HPMA sensor. It is in bootloader mode, so I gotta set up new manager to make sure it's correct. So slab, and then we're doing 1 meg load. Oh, and I gotta set up serial. So set up serial monitor, and we're gonna change that because I originally was using a different port. The NR52 shows up as a different port instead of the slab. So So I'm going to load and monitor and see if this guy chugs along. Cool, it's loading. No, go away. Okay. And I will reset it just to, oh, there it is, but I'll just reset it. Here's a bunch of the SPM stuff. Reloading, we got the HPMA, temperature, humidity, and ppm, PM 2.5. So we're two out of 3. So that's pretty good so far. I'll show what the configuration looks like for this guy, because this one I actually didn't throw up on the slides. But the async API is set up, and you also have just the UART console, log mode, immediate, whatever, log backend to UART, and then just enabling the MCU boot, the bootloader. So nothing too crazy there. And then we're using different P handles for this particular setup, because I know I'm using UART 0, UART 1 for the actual USB to UART connection. But I2C1 for this setup, so, and then UART 2. And we're just setting the speed, we're setting the pins, making sure those things are set up, and also just the pins themselves. We're using bank 0 for both, and pin 0 and pin 1. So, next. So, here's the fun part. We're going to be changing over the this over to vanilla. So you might be asking, like, where the heck are these files? What are you referencing? What is going on? I'm very confused. So in the root of the demo, you have so we already saw these earlier, but you can see the West NCS and West Vanilla. That's all it is. That's all I'm doing, is I'm just changing which one we're looking at, and then we can actually initialize the root folder there. And what it does is just run a West update, and it'll pull all the updates, the dependencies from Zephyr and anything else that doesn't exist. But really, all it's doing is just updating the things that are different compared to the other one. So you can see that it pulled a bunch of stuff with Zephyr. It pulled some different changes with embed TLS, and just also installing some differences in the Python install. So some small tweaks. I'm going to change the board, and I'm going to unplug this bad boy. And LoRa E5 dev board. And fortunately, this particular board uses the same CB2102 USB to UART, so I don't have to change anything else. I do need to change the logging speed though, because this thing is only capable of 115.2 for a baud rate. So, and so we'll do that now. So Newt, setup new manager, we'll be using slab 115.2, and then setup serial monitor. Oh, and that's default 115.2. So build pristine. Let's see if this works without breaking. It should. Fingers crossed. It's chunking along. This by far is like the fastest one, because it's a smaller chip, very basic. So it kind of chunks along. There's only one partition to build, unlike the NR91. So this should be pretty quick. The NR52, you have to build boot, MCU boot, and the application. So it's done. It's done loading. There you go. So we'll load via the bootloader. And this particular board, I did enable it so you can see the red LED turn on when it's in bootloader mode. I actually unplugged. I took out the little the jumper, so I don't even know if it's in bootloader mode. So we'll see if we get it in the first try. But oh, dang! Let's try it again. this can be finicky, and I've had issues across all different boards and platforms. Sometimes it just is in a bad state and it's kind of stuck and you got to reset it. Sometimes you get a power cycle of the board. It really depends. So I'll just give it a reboot. You see, it's loading. So this is all board specific stuff that's happening before the application. And that's just something you can kind of safely ignore. But look, we're getting the same results that we were getting just not too long ago with the other boards. We're getting, the boot message, and we're getting the temperature, humidity, and PM 2.5 readings. So there you go. But really, kind of in summary, this stuff, it can be awesome when you get it running. It's like, I can build my whole application and I can port it to a different device if, let's say, they go out of business, or if literally I can't find any stock, because that is a thing, and I don't think that's going to be going away anytime soon. So that's what people get really excited about Zephyr. That's why I'm very excited about Zephyr. This is why I talk about this stuff every week, because this is the thing that makes it really easy for people who are building hardware, building firmware, building devices that make a difference. These are the things that we get excited about, because it just makes our lives a lot easier. I literally have the same base code. I change some overlays and configurations, and it works on all 3 platforms. They're all different too. They're different processors. They're different architecture types to some extent. So it's like, okay, this is cool. Now, you could even do this if you, like for an ESP32 or like whatever other architectures that are out there, if it's supported by Zephyr and you have a good hardware application layer defined, and you have drivers for UART and I2C, you probably would be able to use this stuff, these drivers, kind of out of the box. All you have to do is just add that overlay in those configuration files, which is awesome. So that's it for this one. I really appreciate you taking the time to check out this session. I know definitely check out Goliath, because theirs is going to be live, so I know everybody's going to be going to the live session, but I really appreciate you checking out this session, and definitely reach out to me if you have questions. Obviously, the code is available on GitHub under this particular repo, and it's in the basic, just the basic sample. And obviously, if you have questions, burning questions, you can. We have a little community going on at community.jaredwolf.com. A lot of people using the NRF 9160 Feather with questions. Even just general Zephyr questions, a lot of them get answered, so you can go there, search for anything that you might be looking for. I hear some people that they're finding their questions answered on Google, but they're getting linked to my blog posts or directly to the forum. So that's really great that it's a resource that is answering questions, which is really cool. Or you can just email hello@jaredwolf.com. And yeah, again, really appreciate you being here, and see you next year, hopefully in person at ZDS 2023. So enjoy ZDS, and see you next time.